Hi. Hello, everyone. My name is Yamen. I suppose there should be a slide coming up to the main screen. It's not mirroring. OK, cool. So there has been a lot of work today, cool work today of movie limb. I will go about MetaArms, which is about body extension by remapping the human body fits into a new artificial limbs as an extension of the human body. So I'm pretty sure you all have had been in the situation that you have hold a lot of objects in your hands and you are missing to do, and you need an extra hand or arm to support you. So imagine you are working on your computer and then all of the sudden you have this spurred, an extra arm that assisting you and supporting you as part of your body. So, and this is what our all research is about. This is what was our motivation. How can we augment our body limits by addressing our body schema limitations? So our body schema has this kind of fixed representation in our brain that represents how many limbs, the extension of our limbs, and etc. If we can alter this, then we can achieve a new forms of body representations. And in MetaArms, we are exploring this form of alteration by substituting one limb, which is the leg, into a new prosthesis arm that act as an extension to our body. So, of course, when we talk about a third arm, of course, we have to mention the great work from Stellark in 1980s, when he demonstrated this mechanical arm that attached to his body. And in his approach, he used an electromyography-based sensing to control this arm, which as a result, it required him, as he reported by himself, years of adaptation and use until he was perfectly able to use this arm as it's his own and perfectly using in coordination with his own arms. Also, there has been interesting work recently from MIT for this supernumerary robotic limbs that are possible to support the actions of the human based on specific context and specific applications. And thus, this kind of design of these arms are driven from the task instead of being driven from the human actions. Also, there has been also really nice work about the sixth finger, which is also an extension of the human hand finger by adding an extra finger, and is correlated in terms of motion of our fingers. And this is being mainly used as assistive wearables. Also from Sang-Woon, he has proposed this programmable joints that can act as in symbiosis manner with our body to assist us. These kind of approaches are great. However, they are mainly correlated with our hand gestures, and thus we cannot have this kind of independency of performing actions without long training to use these wearables. So in our approach, in our proposal here, we want to shift from human-robot interaction into a human-robot integration. And we are looking through like form of substitution of our body modalities through like remapping our body structure. And probably you have already know like about the sensory substitution analogy. So in similar manner, we can probably do modality substitution from one body organ to another in terms of physicality and actions. So here in MetaArms, we want to figure out how we can expand it by metamorphies, the mapping of the body limbs. So this will help us to reduce the training time to use this new prosthesis, and we can actively use it within like probably 10 minutes without training for a long time. Also, like to allow this kind of independency of actions. So we have our own arms plus this kind of prosthesis that we can do a co-action in between them. And lastly is very important aspect in this human-robot integration is to maintain the embodiment and the sense of agency toward these arms. So if we should shift our attention from how we are controlling them into more than themselves. So when for example, when we use a tool, our shift, we are fixed into the effect of this tool instead of how we are acting using this tool. So also similar thing, our body should be reflected in a similar manner. So here we have three design aspects for the MetaArms. First, we have to maintain a close proximity of the design. That is, these arms should be always correlated with our body coordinates. That is when we are always have the same frame and the same coordinates of motion. Second is to maintain direct manipulation and direct control of these arms. So this way we can map the postural as well as the rotational mapping by transferring them into these new hands. And lastly, from ownership perspective, we have to maintain a closed loop system. That is, these arms, we have to have an action and feedback. And this is achieved through both visual as well as haptic feedback, which I will talk about through a data socks, which is an equivalent for the data gloves. This is attached to the feet and provide both the control as well as the feedback to the foot. Here you can see the system in action, and you can see how it is designed as a backpack form with a total weight of 8 kilos. So it is relatively okay for a prototype, and in a total of 6 degrees of freedom per arm. This is for the one in the paper. However, we did another prototype with 7 degrees of freedom to maintain to create more flexibility of the motion. Of course, this backpack form maintain also the proximity of the user, which is very important for us, as well as the coordination of the body motion. And this is for the hand, which is the end effector. We designed it to be an anthropomorphic hand design, so it looks like the human hand, and with 3 degrees of freedom for the fingers. However, they are coupled, which is I will go into why it's coupled as open and close. As well as we embedded into them a set of sensor pressure as well as force sensors to sense when the hand touches something or hold an object. And this is for the data socks. You can see it as technically a socks with actuators and sensors. It can be used with the 6 degrees of freedom position tracking, which is we are using here HEC5 tracker, as well as we use a single bending sensor and a haptic feedback belt that is providing the force feedback. We have explored with dual sensors for the toes. However, it was very difficult, so we reduced it to a single toe measurement. And this is why the hand motion was coupled and all the fingers are moving open and close. Of course, for people with good flexibility of their body, they can use 2 toes or 3 toes probably. Here we can see the system while we are working with some objects like holding cups, objects, balls, etc. And you'll see the user here is coordinating between his hand motion and these robot arms. Like some people might say, oh, he's been using it for a long time. No, I guarantee you most of you can achieve this performance within the first trial. Okay, so before I dig into the user studies, I have to specify some technical details about the system, which is mainly the mechanical latency of the prototype we have developed. There is one crucial issue with any robotic system which we are using with a human, which is the latency, mechanical latency. And here you can see the mechanical latency of the robot is a little bit higher, which is, of course, higher than the user motion, which might affect the performance of the user and the adaptation time. And you can notice the y-axis, which is affected by the gravity, has the highest latency, around 400 milliseconds. So in the user studies, what we aimed for is to measure the performance of the users, the participants, after using the system for a set of time, and what kind of potential learning effect they can achieve after using it, and the fatigue effect of on the user's body when they are using the system, as well as to what level they can feel this system as part of their own body. And this is done through FITS trials, 4 FITS trials. I'll go through about it later. And we have also added a second evaluation for the body coordination to measure the proprioceptive effect of the learning. And then followed by that, we collect NASA task load index of the users as well as embodiment questionnaires, and we allow them to rest for in total 5 minutes. So the overall, we run it for 4 sessions for 45 minutes per participants, and then we try to see to what degree they have achieved the learning. And this is the experimental setup. You can see the user here sitting in front of a screen, and he is using this arm. And all the participants are first-time users. And for people who doesn't know the FITS study, it's basically part of the human-computer interaction to measure the efficiency of the display or the controller, the device that we are using to measure. So we have in total 4 trials for the FITS. And the end effector was we substituted with a pointing device instead of anthropomorphic hand. So just to make sure that the study running smoothly. And here the users are going back and forth between the points. And here we are trying to capture the accuracy and the speed of the pointing. And here we have one intermediate condition that after they run one FITS trial, they have to look at the white dot, close their eyes, and then try to point at it with their arms. And then we can measure the proprioceptive learning of the arms. And this is very important figure for the task load, which is for people who are not familiar with the NASA task load, the higher values actually are bad and the lower are better. So the physical demand after the 4th session increased, which is, of course, because of the repetitive measurements and the repetitive use. And however, the performance, the reported performance by the subject themselves, it increased directly from the 2nd session. After they use it for the first 5 minutes, they found themselves more familiar of using it. And the second diagram is about the reported FITS study, which is, of course, the higher is better here. Some people might argue that this is not very high throughput. However, if we measure it to a previous study for also a 6 degrees of freedom arm, which is reported around 1.08 bits per second, which is kind of comparable value. And you can notice the standard deviation has increased for the last session, which is very correlated with the physical demand of the participants. And here, the reported body coordinate error, which is we are trying to measure to what level the participants were successful to use the arm without looking at it. So it's just through moving their feet and with the haptic feedback as an indicator that they have achieved the task. You can notice that the mean error has been reduced over time. However, the y-axis, of course, has the highest mean error and the standard deviation, which is one thing because of the fatigue, the users has to raise their feet continuously, and the other reason is because of the mechanical latency of the system also can affect this. So this can help us to define what are the guidelines for designing such kind of interaction of wearable arms using the feet motion. So for example, we can increase the gain of the y-axis so to mitigate this kind of fatigue over time. Or for example, we can design based on time slots, for example, how long the duration should be before the fatigue occurs. Some observations we had demonstrated, probably some people have seen this work before as MetaArms. We have showcased it last year in SIGGRAPH 2017, and we have seen really interesting people like using it. So one thing is you want to see like here the coaction of the system. So how the participants trying to use the arms as well as the prosthesis. And here she was also a first trial using the system. She was first trying to learn how to grasp the arms, failure, and then repetitive throwing, and then she was successfully able to catch it. So she adapted to the latency of the system as well as for the positional spatial. And you can notice she eventually shifts her attention from her feet to the arm. So she is kind of like using it as her own arm. Some applications, which is very important here, we have been exploring a form of scenarios. First is substitution scenarios. For example, people who have amputees people or people who had an injury with their hand and they need to use immediately a separate arm. They can use this system without the need of training, like for a month or so. They can just set it up and they can use it in 10 minutes. To be honest, we haven't done any actual trials with people with a phantom limb sensation, but we believe that it can help. And we have had discussion with some people about this. Also, the other topic is augmentative aspect, which is very important for people like healthy people. How can we use this third arm or fourth arm along our tasks? So, for example, we have done like soldering, like playing with objects, etc. And of course, we can customize the arm function based on the scenario. Lastly, which is last month, we have demonstrated at Ars Electronica, there were artists, which we, from academy, we didn't have the chance to interact with. This lady, she was a performance artist, dancer. She has very good balance, so she was able to use the system while she's standing. And she was exploring this kind of symbiosis between this robot and her for dancing performances. So this can be a really interesting topic for enabling new forms of performance. Okay, I think it's almost time. So finally, I'll just do a summary. This system has provided an approach for body integration instead for body interaction using body remapping. We have showcased this exploratory proof of concept system that allow this kind of body mapping, and we have showcased the user studies for adaptation effect of the users. As an outlook, the future work that we are, of course, we want to is first is the mechanical and the design of the system has a great impact on the performance. So, of course, we want to enhance that and decrease the overall latency of the system. And the second one is more from a research perspective. We want to explore the effects of the changes on the body schema from both control and cognitive perspectives. That's all. Thank you very much, everyone. And I hope we have some talk today at the demo session from 6 to 9 at the foyer. So please, let's catch a drink and talk. Thank you very much.
All right, line up at the microphones.
Hi.
Let's start over here. Sorry.
Right. Thank you very much. That was an absolutely fascinating talk. I'm Louis Chuang from LMU München. And I'd like to ask you, just on your basis of experiencing with your participants using the system, how do they transition from doing task switching or multitasking to the final eventual state where they're actually making use of 4 limbs with a single mind, if they're even able to achieve that in the first place? And what are the challenges with regards to training protocol for achieving this transition?
Right. So you are mentioning how, just to clarify, about the coaction and how they can use this in multitasking. Exactly. That's the very important topic here is most of the participants first spent like the first 1 or 2 minutes trying to trial and error until they learn the speed and the motion of the system. And of course, it's not a perfect system yet. So until they mitigate into this kind of design error, like latency and so on, they focused more than on the task proposed. So we also, from our side, we don't tell them to focus on their feet, like about the motion, so they have to learn automatically to focus on the end effector of the arm. And then they were able to coordinate the use of the arms with the task that is being proposed. So most of the people, we have been giving them objects, handshaking them and trying to reach far objects, or like give them to their own hand, and then they have to interact with the arm itself. So they were able to coordinate the motion with their hand motion.
Thank you very much.
Thank you, Louis.
Hey, Daniel Ashbrook, University of Copenhagen. I'm wondering if you've thought about alternate control schemes. So it's great to use your feet to control when you're sitting down, but you have to have pretty good balance, as you noted. So I did some work a while ago with tooth clicking to control an interface. You could imagine like making facial expressions and so on. Have you thought about any of that?
Yes, indeed. This is one of the topic of the transfer, the body transfer. And at the beginning, we wanted first to explore on the limbs itself. But eventually we shifted into why don't we create this kind of overall embodied-driven design approach, that is, we can map some part of the body into a new prosthesis. So we can even define a context-based interaction. Why we used only the leg here? Because, of course, the spatiality and the degrees of freedom, that is perfectly fit to the arms. And because of the, actually, it was kind of easier to adapt than when we used different muscles of the body. We explored using different muscles of the body. However, the leg was the best fit. But of course, for example, we can use the tongue as an extension, or like the lids. And actually, some people have showcased the use of their toes to control the third thumb. Recently, a designer showcased that the third thumb. So yeah, I think there's a lot of possibility to re-engineer the human body.
Cool, thank you.
Thank you.
Hi, Roel Vertigal, Queen's University. I haven't really been keeping up with this field, but I would argue that the more important application, rather than having more limbs, is assistive technologies. And I remember a paper by Melody Moore many years ago where she actually drilled a hole in someone's skull and connected it to a neuron and found that people got a cursor cortex. Can you comment on like the state of the art in that? Have you considered sort of direct neural connections so that you could actually just control the limb as if you're like controlling your own limb?
Yes, that's. Of course, we have considered at the beginning of the design of the system, should we use more invasive approach or wearable approach? Each one has its own advantages and disadvantages. Like, first, we didn't explore much from a neural perspective because, first reason, we don't have enough know-how in this field from our side. However, the other reason is because when we start exploring the use of, for example, EEG from directly extend wearable approach, first it has a lot of noise, and the number of information that we can collect is not sufficient to provide continuous control over the arm. Most of these EEG pairs are classification, like left, right, and then it will require a lot of time to train and use. But I think, yes, there has been work before with monkeys. They embed electrodes directly in the scalp of the monkey, and he was able to achieve the control of the third arm, like to grasp a banana and reach it. So I think it's very doable in the future to have similar thing to directly hack into the human scalp and collect higher resolution information.
Thank you.
Thank you.
All right, let's move on to the next part of the session. One more hand for Yamen.